In this next chapter, we talk about projective varieties, which are a particular class of examples of the varieties that we have seen in the last chapter. To set the stage, recall that affine varieties were defined as closed subvarieties of some ambient space, namely of the affine n-dimensional space. And to get more general varieties, one way we could go is we could glue those affine varieties by hand. We have seen any pre-variety can be obtained like this, but there's lots of disadvantages here. So for example, you have to record a huge amount of data, namely these open sets, and then the maps by which we identify them on the overlaps. We have to check a lot of compatibilities, and then it's quite non-clear how we can check for separatedness in this setting. We haven't really seen any result which will help us there. So instead, what we are going to do is we're going to create lots of new examples by constructing again a nice ambient variety Pn, which is called projective space, which we're going to see in this video. And then we get projective varieties as closed subvarieties of this Pn, very similar to this setup. And then this ambient variety also gives us things like coordinates, which we're also going to see today, which we can use to describe these projective varieties. So this will help us cover lots of interesting examples. And in fact, it's hard to construct a variety which is not an open subvariety of a projective variety, so not locally closed in some projective space. First one was constructed by Nagata, but actually we're not really going to see this in this course. We're basically going to restrict these open subvarieties of projective varieties. And so in this chapter and the next, we're actually going to develop this language for projective space and these projective varieties from first principles. So we're going to start again really at the bottom and construct things as sets, and then we give them a topology, and then we make them into ringed spaces by defining a structure sheaf. We're going to see a very similar story to the things with affine varieties. The advantage is that having this language is then very useful for concrete computations, and also we can kind of recall what we did in the lecture so far and seeing these steps again in a slightly more general setting. Okay, so this was the big picture. And now the motivation for the concrete definition of projective space is maybe looking at this picture here. So this is the classical solution you see here, v of xy minus 1. So the classical hyperbola. And one thing that we can see is that, I mean, these solutions, at least in the real picture, you can see that we can go on and on and on. We can make x very small, y very big, and the solution goes essentially to infinity. It goes on and on and on. That means, for example, in this case, that the solution set is not compact. Of course, we can have a sequence on this set which converges to infinity, but infinity is not really contained in A2, so it doesn't have a limit in the classical topology. And to solve this, you can use this idea of projective space or of projections. And so the idea there is the space A2, which as I said is just k squared, right? The base field to the power 2. You can set this inside a space of one dimension higher, namely k3, as the set where the first coordinate is 1, like this. And so it's basically like a screen, like in a cinema. And then you have a projector at the origin, and it's starting to project images onto the screen. And so, for example, if you want to get this, this vanishing set here, then any point on this solution set would correspond to a line going from the projector, so from the origin, to this point here. So the solution x, y corresponds to this line spanned by the vector 1, x, y here, because this is placed at the height 1 in the first coordinate. And then what we see is, Now, if you look at these green lines, as the point moves, the line becomes steeper and steeper. But I mean, it's not diverging in any sense, but it's just kind of getting closer and closer to the line, which is just the line which is parallel to this plane in the same direction as the y-axis. And so you could say these solution lines here converge to this line here, which is spanned by the vector 0, 0, 1. And if we then look at these solution sets in this set of lines, then we get actually a very nice set. And so, okay, I don't know how motivating this was, but I think this is in fact where the space name projective space comes from. Namely, it comes from such pictures of projecting from a point onto some plane. And then the hard definition here in this video is that of projective space. So for n, a natural number, we define projective n space, and sometimes you specify k to make sure that you say which coefficients you use. You define it as the set of lines L inside k to the n plus 1 lines to the origin. So in other words, L is a one-dimensional linear subspace of this vector space k to the n plus 1. That's it. As a set, we're already done. We have defined projective space, and you see all these green lines, of course, they're elements of P2. You have to be careful. There's this shift here. So because they sit inside K3, they're elements of P2. Okay. And to make this a bit more concrete, so a priori, I mean, working with these lines is kind of hard because we really like to have coordinates. And we can do that. And so we can describe some coordinates on the projective space. Namely, we just observe that any one-dimensional space L, as before, can be specified by giving a generator of this vector space. So a single generator would be some vector in k to the n plus 1. And well, it should actually span a one-dimensional space, so it should not be 0 like this. So each L can be described by such a vector. But of course, the vector is unique. You have a choice which generator you take. And two such vectors span the same space, of course, if they're linearly dependent. So in other words, if they're multiples of each other, scalar multiples. And so as a set, as a second description, we can describe Pn as the set of all vectors x which are non-zero up to the equivalence relation, which says that a vector x and a vector y are equivalent if and only if there's some scalar inside k star, so a non-zero element of the field, such that xi is equal to lambda times yi for all I. So one is a multiple of the other. So that's a second description, and now we can really describe points here by giving an equivalence class of a vector. Right. And sometimes this is also written, so in many books you will find this as saying this here modulo k star, because these lambdas in k star, they control which vectors are equivalent. In fact, I mean, if you know these terms, you see that this k star, the multiplicative group of k, acts on this space k to the n plus 1 minus the origin as a group action. And then this here is the quotient of this under the group action. And we denote the equivalence classes of these points with this notation here. So the equivalence class of such a vector is again in round parentheses, but instead of having the commas here, we place these kind of columns. And this should remind us that basically what is preserved in these coordinates is that the ratios between these entries here are preserved. We're going to see this in a second. Let me just comment. First of all, these entries of the vector, they are now called homogeneous coordinates. We're going to see also where this homogeneous comes from. And what you should remember is they're not all allowed to be 0. because we always have we exclude the zero vector. And these are only well-defined up to simultaneous scaling. If you look in other books, you will also find different notations for this. So sometimes this is called with brackets like this, and still the colons, or brackets and commas. So basically every combination is possible, except for round parentheses and commas. This is reserved for the affine space. And just to have a baby example here, so inside P2, then we have to specify 3 coordinates, 2 plus 1. And then, well, we have, for example, this point 5 minus 2, 3. And then this is equivalent to the point where you scale all of these things. So for example, you can scale them by multiplying all of them by 3, and you get 15 minus 6, 9. Or you could scale them by, and this is an operation which we're going to do a lot, we can divide by one of the entries. This makes that entry 1, and then the others become something. So in this case, minus 2 over 5 and 3 over 5. And what I meant here by the ratios are conserved is that, well, if you divide this by this, 5 divided by minus 2 is, well, minus 5 over 2. And if you divide 15 by minus 6, then you also get minus 5 over 2. And the reason is, of course, in this quotient, if you multiply both of them by the same number, then taking the quotient removes that number again. And so that's one kind of motivation why we place these column vectors, because the ratios are conserved. So this is a bit about the homogeneous coordinates on here. And next we're going to see that the projective space actually contains the affine space that we like as a subset.